Hi. It was, well, I mean, I guess
please introduce yourself.
Oh, yes, sorry. Pablo Meyer. I'm a part of the organizer of DREAM and from IBM Research, but I didn't participate in this challenge, so I'm getting the whole picture now. So, I mean, of course, the problem is, the fact of trying to differentiate between clinical data and the SNPs. And one of the questions is, would it be possible to actually correlate the clinical data to the SNPs, then take out that, and then see if with the SNPs that don't explain the clinical data, you could try to predict, what you would expect to be more genetic, more depending on the SNP.
I think that's an interesting question. I think actually what many of the teams did was the opposite. So they looked at the correlation between the clinical.
But it seems to be so overwhelming that the only way to try to find a correlation is to actually try to get rid of the clinical data, and then with whatever's left, can you still predict something? I mean, I guess that maybe.
Yeah, I think that's an open question. I think whether genotypes that affect, for example, baseline disease activity score are the same or different SNPs that might affect change in disease activity score is an open question.
Hey guys, Alvaro Gonzalez, Memorial Sloan Kettering. I know the genomic information didn't help a lot in prediction, but I couldn't help but wonder if any of the SNPs that ended up being good predictors, especially for the non-responders, did you guys gain any biological insights? Was any of them somewhat related to the arthritis, and was it something that you guys hadn't read about, or was a little surprising?
So we did literature mining to select the SNPs that are actually related to the anti-TM treatment. So we actually end up with 10 to 15 of them. So that works in at least these two data sets. So you could say at least they are reported to be, so they should have some clinical insight because some other people already reported, and it also works here. So, and that is only for the SNP. So we did a test that we using cross-validation, and we use the leaderboard. We test whether adding this literature reported SNPs will further improve the performance. So because it improved the performance, so we assume that they got this this biological insight is correct.
Well, at the beginning, we tried just using these protein-protein interaction networks, just doing a selection, a driven selection using the information, biological information provided by networks. But at the end, we didn't use this criteria to select. But it could be used. So if some of the candidates could be confirmed in the corona dataset, then it would be nice to look to which protein they are and what are they doing.
So there's Steve Kornblau from the MD Anderson. So there's a potential problem, and this rears its head in the leukemia one that comes up later this afternoon, in that you guys seem to be considering that all rheumatoid arthritis are created equally. And there could be different mechanistic underpinnings. Simplistically, you could have overimmunity in one sense, a failure to decrease an inflammatory response on another sense. And when you merge them all together, you're looking for things that are universal across the whole disease, whereas the predictors for responsiveness and non-responsiveness might be very different within different subsets. So stepping back, was there any effort made to see if there were different subsets of RA within there that should be analyzed separately as opposed to looking universally?
I completely agree with you, and I think that's something that needs to be looked at in any of these clinical data sets that we're looking at. Not on our end, not from the little bit of clinical information we have, but my understanding of your approaches is that they actually do look for predictors, well, using the same set of SNPs. You're looking for predictors within individuals who are most similar to the people that you're predicting, right? So that is sort of built into the algorithms in a a non-biologically intuitive way. But yeah, something that needs to be looked into.
I have a two-part question for both of you. The backdrop is the connection between sample size and the concept of infinite challenges. So is it possible to assess what data in terms of numbers of patients might have been helpful to have? That is, when you look at what you had, is it possible to extend to a, hey, if we had 20,000 or 100,000, we could do this or that, and what do you think that number is? And the second is, later, Paul Boutros is going to show some nice example. A number of groups got together and realized that if you wanted to accelerate the adoption of new standards, that one way of doing it is having a more continuous challenge, not one that says we're going to this date and we're stopping with this data, but one where the data flows in all the time, and as the data flows in, the answers get better. So question now is, do you think you know what sample numbers you wish you would have had to bring in some of the robustness that you might be missing? And the other is, I noticed that the drugs stood out as one of the parameters. Wouldn't it be nice for patients if everyone who had arthritis had a way to contribute somewhere what their scores were on certain drugs before or after using those drugs? And you might be able to get a lot of samples. If you're not going to even use the genetics, you might be able to do it just from asking people to go online and give data. If you need the genetics, you could add that. So you get the two questions. One has to do with what's the optimal number, and the second is, have you thought about sort of an RAX challenge where you let patients start flowing the data in?
About the first question. So in this challenge, we have 2,000 samples, and because we built 3 drug-specific groups, so actually we have like about 700 samples for our model. So based on our observation, like mainly from the cross-validation to see like what is the performance changes when we just add more samples. So I'd like to say if the sample size is something around 1,000, it should be quite fairly enough. Like 200, 300 samples don't seem like a good number. 700, like for this case, it should be fine, but maybe like, but yeah, of course, we're adding more samples, we're getting more, getting better predictions, yeah. For the second question about the futures, well, I'd like to say, like, for example, the SNPs, like, is kind of weak predictors. So probably, like, in the future, if we can add something like expression data, something like that, that's much more stronger genetic features, it could be helps. Yeah.
Yeah, about the data size. So we have not thought about it. Of course, as bigger it is, better. But so as we have showed you in those distribution of correlations, as just the data set is smaller, the variability is higher. So as so I thought the size of the data set could be calculated on the p-values we have obtained using the Fisher test or other tests, and to calculate how many patients would be needed to make these p-values more robust, because most of the p-values were not robust at all. It was 10^-3, 10^-4. It's just having this number of SNPs and patients. This was not significant. And I didn't get exactly the second question.
Hi, this is Divya Mistry from Iowa State University, and I was actually curious about the sample question, which you just answered. So I'll ask something else I was curious about. So the methods that both of you chose, the Gaussian process regression, it's a method I feel like I would have easily overlooked. So how did you decide on that method, and sort of what else did you try that you eliminated? Like why? I know you tried SVM, but sort of other things that you may have tried, and why? What was it about this GPR that worked well for you? Thanks.
We actually try different methods, but it don't work as good as Gaussian process regression. I think the main advantages of Gaussian process regressions are it's not like linear regression. You don't try to just fit a function to the to doing the predictions. It only try to find like the close the patient that has the most similar with the target. So using this subset of patients to doing the predictions. So that's and also because the Gaussian process regression can take into can downweight the samples that are like quite similar with each other. So something similar like the mutual information. So because we got like this data from several cohorts, we could expect that the cohort data, like within this cohort, this data could be something similar. So the Gaussian process regression can actually handle this cohort effect quite well.
Well, just from in our team, just the selection of the classifier was done on the experience, on the one on the results we obtained in our training dataset and the results we observed in the leaderboard. So using the Gaussian processes was the most robust one and the one in which the expected results were closer to the observed results. So it was just a matter of testing the classifier and selecting this because this worked better.
So I'm curious, given the power of the clinical variables to predict response, which of the 6 clinical variables gave you the most predictive power, which were most heavily weighted in the classifier, and why? It's always interesting to know.
So the question is, which one of the attributes is providing the most strong signal? It's just from we think is that just the baseline dash. So as this is the correlation between baseline dash and the delta dash, and the correlation just in the training dataset is close to 0.40, and it was providing the most strong signal that may be modulated with the age or with other clinical attributes, but the main weight was this one. And in the second sub-challenge, again, the baseline dash could provide some of the most strong signal.
So when we're doing the cross-validations in the training data, if we only have we separate the separate the samples into drug-specific groups. So for the rest of the features, we first test like the baseline DAS28 score, and we found that if we only have that in the training data, we can have a correlation of about 0.45 or something. And if we add add age, gender, and whether the patient has other co-therapies, that 3 predictors it will improve the correlation to something like 0.48. And if we add the SNPs in, so that becomes 0.54. So yeah, the baseline is the most important one. Well, because when we build this model, we pick the SNPs. Like the SNPs we use is drug specifically. So, but it's like if we only have clinical features, that already has something like 0.48 correlations in the training. So actually, if we don't separate into 3 drugs, it should still works probably fine. So, is that what's your question? Okay.
Witold Trudnicki, University of Warsaw. I have 2 questions, actually. I don't know if exactly to you or to organizers. One, I'm interested if you found the same features. You have worked independently, and whether the features that you found as predictive were the same. Another question is also, say, even more to organizers. If it is possible to have this data challenge, that this challenge have to be running after it is officially closed, just to try new methods that were developed in exactly the same setup as was designed for the challenge. So you have the leaderboard, you have the same training set, and you could test new methods. Because I didn't participate in this challenge, but I'd like to check my methods that I developed for another challenge, newer challenge on the same set. So this is the question.
Yeah, we'd love to give you a crack at it. So we have considered that, leaving the leaderboards and the scoreboards open. There's some logistical issues around that. So we've been assessing whether it would actually be useful to the community if it was worth the effort to do. So that's really useful feedback from you that it would be in your case. In terms of the commonalities and the features that were selected, we actually did look across all of the features from all of the 8 teams that went into the community phase. And yes, there's certainly commonalities in there. I mean, in particular, people are picking from the literature based on what SNPs have been shown to be involved in previous studies. So certainly those show up repeatedly. But there are also substantial differences across the groups as well. And we actually haven't spent much time taking a look at what the biological meaning may be there, but it's certainly something we should look at. Gustavo, do you have one last question?
Yes. I wonder whether Gustavo Stolovitsky, IBM Research, I wonder whether there is a merit in thinking of stratifying differently. Did you guys try any by clustering and try to see whether there are SNPs that are specific to subgroups? For example, you showed, I think, Fan, that different drugs had different performance in different drugs, right? That's a way of stratifying. So might it be that the SNPs don't give much information because we are not looking at the SNP specific for some stratification?
Well, in the community phase, we try to stratify by age or by the baseline DAS, so just to remove this noise. But the thing is that as we stratify, we reduce the size of the data set, so the p-values and the association measures we obtain are less significant. So then we didn't know how to select from those. So we tried, but they're reduced in the sample size.
Yeah, we didn't use any the math this correlated try to find some of the orthogonal features. So we didn't use any method just to determine the SNPs from the different background groups. Yeah. Only the drug types. Yeah.
All right, well, I'd like to again thank our 2 participants, our winning participants. Thank you for your efforts on the challenge and for coming here and describing your methods to us.